All right, thought I would go over 25-minute FRQ number 1. We are given this table of data. We have values, some values of x, g of x, and g prime of x. And it says that the functions f and g are twice differentiable. We'll probably need that at some point. That's a specific piece of information that we can use for MVT, IVT, things like that. Selected values of g and g prime are given in the table above, and the function f is defined by this. So when you guys get your problem for your 2020 exam, know that you don't want to just spend 10 minutes looking at the problem, but you do want to read it and make sure that you get the information from it that you'll need in the problem. Whenever I see that f is defined to be something with an integral, I will go ahead and find f prime and f double prime in case we need those. Those are usually kind of quick to find. So for f prime, I begin with a 2 and I take the derivative, and the derivative of 2 is just 0. And then I go to this integral, and the derivative of this integral is, I see the 3x up here, and I have to begin by taking its derivative. So the derivative of 3x is 3. And then we are going to replace t with 3x. So this will be g of 3x. The 0, it would be minus the derivative of 0, which is just 0, times g of 0. So that last term will be just 0, okay? Take a second to make sure that you can do that. As long as this is a constant, that last term will just be 0, because when you take the derivative of any constant, it's 0. For the second derivative will be, all right, we have the 3, which will be multiplied by the derivative of g of 3x. Now the derivative of 3 of gx is g prime of 3x times the derivative of the inside, right? And the derivative of the inside is 3. So I'm going to be multiplying that derivative times the 3 that's out front. So this will be 9 g prime of 3x. Make sure you keep your argument. Okay, part A. Explain why there must be a number c in between 0 and 9 such that g prime of c is a third. When I see this, usually when I see the g prime, I think, oh, we're talking MVT. And I'm going to use values of g and use MVT to show that there must be this value of c. Now in this case though, since they give me g prime of x as well, this might be an IVT problem. If 1/3 is in between 2 of the g prime values, then I could just use the IVT. But when I look at this, 1/3 does not appear to be in between any of these g prime values. So it's not going to be IVT. I am going to use MVT, and I just need to find, remember we're looking for delta g over delta t, or x in this case. We want two x values that make delta g over delta x 1/3, right? And it didn't take me long to go up and spot it. I'm not going to be using those two, so it kind of leaves me down to these two. And sure enough, -1 minus -2 is 1. 3 minus 0 is 3, and so that does give me a 1/3. So I need to use 0 to 3 for my delta g over delta x. And then the MVT will work there. So to use MVT, I need to first say that this function g is continuous on the closed interval and differentiable on the open interval. Since we're using 0 and 3, specifically we need g to be continuous from 0 to 3 inclusive and differentiable from 0 to 3 not including 0 and 3. Since we are given that g is twice differentiable, we know that g is continuous and differentiable for all values of x. So that's what I'm going to say. G is given to be twice differentiable. So G is both continuous and differentiable. And when I say that, I'm saying that it's continuous and differentiable everywhere, so of course it is on the small intervals that I need it to be. All right, next up, I need to state that this delta G over delta X is equal to 1/3 at those values of X. So I'm going to say G of 3 minus G of 0 over 3 minus 0 is equal to, so G of 3 was on my -1, G of 0 was my -2, and this is equal to 1/3, which is what I needed it to be, right? So after I state those two, I can say, therefore, there must be a C in between 0 and 9 such that G prime at C is 1/3. So I'm going to say it this way, I'm going to say by MVT, but you don't have to say by MVT, you can just say therefore. By MVT, there exists C in 0 to 9 such that G prime of C equals 1/3. You do not have to use these symbols. I like to abbreviate those symbols, but you don't have to abbreviate those symbols. Or you don't have to abbreviate those words. You can just write out the words. Okay, next up, part B. We have this little integral to evaluate. And I notice that we have f triple prime of x, and we have this 40x. The 40 is not a problem. I could take that outside if I wanted to, right? Or you can just leave it inside. It doesn't matter. But the 40 definitely is not a problem. But we have x triple prime of x. So because I have this x out here, I'm going to need to use by parts integration. So I'm going to go off to the side. I'm going to let u be my x in there. In fact, I guess I'll let u be 40x, and then I'll just keep the 40 where it is instead of taking it out. Either way is fine. So du will be 40 dx, and my dv will be everything else here, so it's my f triple prime of x dx. To get v, we're integrating both sides, and the integral of f triple prime is f double prime, like that, plus c, but we have a definite integral, so we don't need that, and we wouldn't add it at this point anyway, right? So my integral becomes, okay, uv, so u times v, so 40x f double prime of x, and we're going to evaluate that from 0 to 3, minus the integral of v du. Here's where I'm going to take that 40 outside of this integral, and then I'll just have the f double prime of x dx, and we're evaluating that from 0 to 3. Okay? Now, this is easy. We just plug in the 3 and the 0. Here, we need the integral of f double prime, and the integral of f double prime is just f prime. So all of a sudden, this gets pretty easy. So I'm going to go ahead and put the 3 in for x. That'll be 120 f double prime of 3, minus, when I put the 0 in, I'm going to have 0 f double prime of 0, minus 40 times, okay, f prime of 3 minus f prime of 0, if we use the first fundamental theorem there. Okay, and now I just need to find out what is f double prime of 3 and what is f prime of 3 and f prime of 0. Here's where I'm going to come up to my little definitions. So let me write those down here again. So we found f prime of x to be 3g of 3x, right? So f prime of 3 f prime of 3 will be 3g of 9. And g of 9 from my table, g of 9 is -1 over 20. So that can go in for that f prime of 3. And f prime of 0 will be 3g of 0. And g of 0 was my -2. Like that, so that can go in for f prime of 0. And we also set up above that f double prime of x was that 9g prime of 3x. So f double prime of 3, that's the value that we need, will be 9g prime of 9. And g prime of 9 from our table, g prime of 9 is 3/4. So we can go and put all those in. We have 120 times f double prime of 3 was 9 times 3/4 minus 40 times f prime of 3 is -3 over 20. And then f prime of 0 is -6. So that would be a safe stop spot, and I think I'm just going to leave it right like that. Okay, part 2. Let's take a look at this. Okay, using a right Riemann sum with 3 subintervals indicated by the table above, approximate the length of the curve g of x from 0 to 9. So first of all, let's write our integral for the length of g of x from 0 to 9. And the length of g of x will be, it's the length of a curve, so 0 to 9. And our formula for the length of a curve, it came from the Pythagorean theorem when we developed it back when we were learning this, is the square root of 1 plus the derivative of your curve, of your function, and the derivative of our function will be g prime, and then we square that, dx. So that is that's the integral that we're going to approximate using 3 subintervals and a right Riemann sum. Okay? So we're approximating this. So from 0 to 9, the first interval will be, the first base length will be 3 minus 0, or 3. So the first base length is 3 minus 0, or 3. Okay? The height of this, the base length of this rectangle, the height of this rectangle will be this square root. In place of the g prime, we need to use its left value. So in this interval, the leftmost value is 4. So it's going to be the square root with 4 in place of g prime of x. So square root 1 plus 4 squared. That's the first term in this Riemann sum. Now we go to the next interval. The next subinterval is 5 minus 3, which is 2. And in place of the g prime, we're going to use the square root of 8. So we'll have 2 square root 1 plus square root of 8 squared. And yes, you can just put an 8 right there, but this is good. I like to, especially when we're writing the terms, I like to put exactly what these data values are. Okay, so whoever's grading this can tell exactly where those terms came from. The last subinterval will have base length of 4. 9 minus 5 is 4. Square root 1 plus, and then that g prime value, the leftmost g prime value there is square root of 3. So this will be square root of 3 squared. And that is the right Riemann sum with 3 subintervals that approximates the length of that curve. So I'm definitely just going to stop there and not do anything with it. safe stop it. Okay, next up, part D. It says let P sub n of x denote the nth degree Taylor polynomial for f about x equals 0. Find P sub 2 of x. So we want to find the second degree Taylor polynomial for f about x equals 0. It's a little bit, let me focus that a little bit. Okay. So for any Taylor polynomial for f about 0, we start with f of 0. We need f of 0. So let's go back to our little information here. F of 0, we need to go find f of 0, right? So I'm going to go off to the side here and find f of 0. F of 0, we are going to replace the x with 0, right? So I'll have 2 plus the integral 0 to 0 of g of t. Well, that integral is just 0, so the function value at 0, f of 0 is just 2. Okay? And now we go to f prime of 0. So f prime of 0 will be 3g of 0, which is 3 times, and g of 0, come down just a hair, g of 0 is a negative 2, so g prime of 0 is negative 6. And then we need to go to the second derivative because we need the second degree Taylor. And the second derivative of f at 0 will be 9g prime at 0. And g prime of 0 is 4. So f double prime at 0 is 36. So the second degree Taylor, they tell me what to name it, so I am going to name it. If they tell me to name it, I will name it. Is equal to, we start with f of 0. F of 0 is 2. Then we go to the next term, and the next term has negative 6 in it, so minus 6. It's the first derivative, so it's divided by 1 factorial times x minus the center is 0. You can just put that as an x, of course, to the first power. And no, you don't need the 1 factorial because that's just 1, and you don't need this 1 exponent because that's still just x to the first is just x. But I'm going to write it there just to drive home that pattern. And then we go to the next derivative, it's 36. Don't forget to divide that by 2 factorial, and then it's x minus 0 squared. This would be a safe stop spot. If you just can't stand it, and please be able to stand it, but if you just can't stand leaving it like that, this would be 2 minus 6x plus 18x squared. Okay? If this was a problem where we were going to use this, then I would go ahead and simplify it. But since we're not going to have to use this, I would just leave it like that. Okay? Well, I take that back. We did use it. We are having to use that in part E. Okay, consider this geometric series. This is a geometric series, okay, whose first 3 terms are defined by the polynomial p sub 2 of x, found in part D. Find the sum of this series when x is 1/6, or show that the series diverges. Okay, well, this is geometric, so we know what will make it converge or diverge. It depends on the value of r. So let's write this out. It says that this series has first 3 terms of 2 minus 6x plus 18x squared, as obviously alternating in sign. And so that is the series, okay? When x equals 1/6, let's find the series. When x equals 1/6, the series is now 2 minus 6 times a sixth, and 6 times a sixth is just 1, plus 18 times 1/36, and that's 1/2, etc. Okay, let's take a look at this series. Our value of r what we're multiplying each time to get to the next term, our value of r is going to be -1/2. Our first term is 2. So this series has sum a over 1 minus r. So find the sum of the series when x is a sixth. That's what we did. We found the sum of the series when x is a sixth. And that's it. I would totally safe stop that. Okay, good problem. Let's see what all this accomplished. We had an MVT, we had a by-parts integral, we had a Riemann sum, and we had to know the length of a curve. We had a Taylor polynomial, and we had a geometric series, and we had to find the sum of a converging geometric series. So this one problem had a lot in it. I would consider this a 25-minute problem. I see by looking at my little clock, it took me 21 minutes, and that was with talking an awful lot about it. So hopefully you could get this done in under 25 minutes.